Swayam Prabha. Digital India. Educated India.
In the last class, we started looking at how peptide structures can be determined by NMR. We looked at how nosy and rosy peaks are integrated, and once the rosy and nosy peaks are integrated, they are converted into distance using the relation that intensity is proportional to 1 over r to the power 6. But usually we do not do that practically. Practically the distances are never calculated exactly, but they are estimated in a rough manner. So, typically what is done is that you consider a strong intensity peak as a short distance, let us say between 2.5 to 3.5, a medium intensity you consider it as a distance having 3.5 to 4.5, and a weak peak will be beyond 4.5 to 6. So, this is what we will see now in today's class. So, you can see the typical protocol is shown here. So, as we discussed, first the nosy intensities are converted to distance, and we use the word constraints. And why is that called a constraint? The constraint is called because we are now going to determine a 3-dimensional structure using distance as the information between the atoms. So, therefore, the structure will be constrained to satisfy these distances. Another type of constraints or information which we give is the J3 bond J coupling between hydrogen atoms. So, typically this is the backbone phi angle, psi angle, and it can be for the side chain chi angles and so on. So, this is another set of values which we input to the computer program which does the software, which does the structure determination. So, this is what is shown here. So, we basically do what is called as a molecular dynamics calculation carried out. So, what is done is you take a random structure first. Okay. So, random structure is because initially we do not have any information of the structure of the protein, because that is our goal. We want to determine the protein structure or peptide structure. So, we do not have any information on how the structure looks like. So, we can start from a very random coil structure, and then you start giving these constraints, and based on these constraints, that is distance and angle, the program will now try to get to a structure, arrive at a 3-dimensional structure which will satisfy these constraints. So, the final structure which is calculated is such that all distance and angle values which we have given as input are satisfied as much as possible, because it is never possible to completely satisfy all distances. The reason being, many a times the intensity is what we measure from rosy may not be the correct intensity. It may be distorted because of overlap of peaks from other residues. It could be because of the noise problem, it may be a weak signal to noise and so on. So, therefore, the distances which we get from the intensities are never the correct distance values, and therefore, it can be not, it is not possible that all distances are satisfied for a given structure. So, what we do is we try to satisfy as much as possible, and those which are not satisfied, we use the word violation. So, we say that these distances are violated, some of them. So, we look at those violations, why are those violating, what is wrong with those distances, why did they get not satisfied, and what are the angle problem values, what values problem with the angle values, why didn't they get satisfied and so on. So, that detailed analysis has to be looked again. So, that means one has to go back to the spectrum and look at those intensities and recalculate distances. So, this is a iterative procedure which is depicted in this picture here. So, as shown here, we start from a random structure, random coil structure, and then we input this information of distances, where Rij is the distance between atoms I and J, two hydrogen atoms. Remember, we are working with hydrogen distances, hydrogen atom. So, two hydrogen atoms I and J, their distance between them. And how do you get the distance? The cross peak in the rosy or nosy spectrum between these two atoms Ij that intensity gives you this distance. And similarly, we get the phi and psi values based on certain experiments we discussed, like J, H and H alpha gives you the angle phi and so on. And we input all this and we carry out what is called as simulated annealing. Simulated annealing is basically a protocol for in molecular dynamics simulation, where you carry out first you generate a random structure at high temperature and then slowly cool it down, and while cooling it is constrained to these structures, these distances constraints, and it finally gives you some structure which will satisfy or which is trying to satisfy all the distances and angles which you are given. And the energy, there is also energy minimization step, so that the inner structure which you get in the end is energy minimized. So, this is the typical protocol which is followed in any structure determination program which uses NMR data. And what happens is, because we are trying to satisfy a distance and a constraint, we do not know the structure as such, so that is why we do not call this as a structure. In many literature, many papers and many groups would tend to refer to this as a model, because it is not a structure. We never really know the structure of the molecule, we only know a model representative which looks like that structure. So, why it is called a model? Because we are building a model based on the distance values and the angle values which we get from the NMR data, NMR spectrum. So, based on those values we are building a model which kind of satisfies and may look like a structure. So, we remember we never get the exact structure because NMR can only be is a derivation, we are deriving the structure based on some distance information. So, what is done typically is we do not start from a single structure, we generate hundreds of random structures, because remember random structures can be any number, it can be any randomized structures. So, we can typically we generate about 100 randomized structures, then each of them is subjected to this molecular dynamics analysis simulation annealing, and slowly the distance values are given for each of these 100 structures, and you finally get 100 final structures. But all hundreds will not be correct, because in many of the 100s or many out of the 100 there will be violations of distance values. Violations means the distance values which we give may not be satisfied. So, therefore, we take the best out of those 100 structures. So, this is what is shown here, that all structures are basically subjected. So, we call the word restrained simulated annealing, and best 20 structures are taken as shown here. So, the best 20 structures typically mean 20% structure, means 20 out of 40 out of 100, sorry, this is actually should be 40%. So, let me correct this, it is 20 to 40%. So, that means if I generate 100 random structures, I will take the best 40 structures are taken, and those best 40 structures out of 100, all of them can be considered to represent our structure. So, therefore, when you look at NMR data which is presented in papers and on the websites, you will see that they do not show you one structure, they will show what is called a bundle of 20 to 40 structures. A bundle means an ensemble, a collection of 20 to 40 structures, because those collection they have been arrived by generating 100 random structures, each one subjected to these conditions and energy minimized, and out of those which are having the least energy or least violations, least number of violations are considered as the best structures, and then based on that those 20 to 40 structures are collected, and all of them are now equally good to represent the main structure. So, therefore, it is NMR compared to other techniques like crystallography, you do not generate one structure, but you generate a set of structures, some ensemble or a bundle of structures, all of which have been derived starting from random structures, and all of which have been subjected to the same constraints of angle and distances, and out of all the random structures the best ones are taken. So, this is the typical protocol of NMR structure determination by NMR for peptides, proteins, and for even for nucleic acids and so on. Whenever you use NMR data based on NOESY, this is usually what we do. And but one thing is, once you have the structures determined, The next question which comes to mind is how do we know it is correct? Okay, so remember this is a model building process. We have built a model of the protein structure based on the information we have given is angle and distances. So, the model can be wrong if the distance and angles are wrong, angle meaning torsion angle. So, how do you find out if the structures are correct what we have generated? So, this step is known as structure validation. So, we validate or we verify whether the structures we have derived is correct or not. So, number one thing to verify the structure is to find out whether it satisfies a general structural in general whatever the structure of peptides and proteins which we exist in our literature in database, whether our new protein structure satisfies the general constraint of those protein structures. What does it mean? This means that it should at least have the say bond lengths and bond angles within the limits which are given in the literature for the standard bond angle and bond lengths. So, that should be satisfied. So, there is a required values are given in literature or in database. So, all the bond angles and bond lengths in our peptide which we have solved the structure should satisfy those values. They cannot be arbitrarily different from these bond lengths and bond angles which are known in literature, because in database typically these are derived from high resolution X-ray crystal structures for a large number of proteins. So, it has been now found out that the bond lengths will typically fall in a particular value for carbon carbon single bond, carbon nitrogen double bond, so on, and the partial double bond of the peptide and so on. So, these lengths should not vary beyond a certain limit. So, within that limit if it is satisfied, that is the first check which is done. Then the second check which we do to verify if the structures is good is that all the distances which we have given, we use our distance constraints. So, all the distance constraints that we have given should be satisfied and there should be not too many violations. Violations meaning that it is not following the value which we have given. So, that means let us say between two atoms A and B I have given distance of 5.5, but in the real structure let us say it is coming to as 7.5. So, what basically it means that the limit should be 5.5, but it is not being satisfied. So, that case we call it as a violation, and that is a very big violation. For example, 5.5 to 7.5 is like a 2 Armstrong violation, which is huge, and that should not have happened. That means something is wrong with some other distances, or there is a particular distance. So, one has to go back and look at his data and then recalculate distances or relook at the assignments. Many a times typically what happens is the assignments means given Rij, the distance between two atoms I and j is calculated based on the cross peak between the two atoms I and j, but the cross peak may not be correctly assigned. So, in that case you result in a wrong distance value, and that can also create problems. The other thing which is checked is that the backbone dihedral angles, which is phi and psi, that is for the backbone peptide bonds surrounding the peptide bond, they should fall in what is known as the allowed regions of the famous Ramachandran plot. So, Ramachandran plot is a plot of phi versus psi. This is a very standard plot you would have seen in textbooks and in papers. It is a standard plot of a phi versus psi plot, and it is said that for a given beta alpha helix or beta sheet, one should have a particular value of phi and psi for the particular for all residues. So, those regions where they should fall is known as the allowed regions. So, if the phi and psi value for a given amino acid in your peptide falls outside that region, that is called disallowed region. And why it is coming in the wrong region? It is because there is something wrong with the structure, and therefore, it is adopting a wrong conformation, and therefore, that is not possible if the conformation was right, and therefore, that region is known as disallowed region. And that also has to be checked, that the majority of the residues amino acids in your peptide should fall in the allowed region. And then we also look at what is called bad contacts. Bad contacts are means two atoms are coming very close to each other within their van der Waals distance, and that cannot happen because that will lead to repulsion, but that aspect since we have given a wrong distance value, that aspect does not come into play in the calculation. So, therefore, they may end up coming very close, which should not be the case. So, this all these checks have to be done to make sure that our structures are not too much away from the required constraints or required values for different distances, angles and so on. So, all these checks are done very automatically nowadays, automated way by software programs, and typically the names of software programs are given here. There is a very famous program called ProCheck NMR. So, ProCheck is used. In fact, when we deposit our structures in PDB, in the data bank, PDB also has a inbuilt validation software. So, that is also it checks before you finally deposit the structure to the data bank. So, this is the structure validation we have looked at very briefly. There are many more parameters has to be checked, but these are the major ones. So, this brings end to this part of the course, and we will now move on to the next part, the last part of the course, where we will look at some advanced topics in this course, and this is where we will see that the following topics we will go one by one through this, and these are basically either using 1D NMR or it can be using 2D NMR, and we will see how these are basically applied. All of them in fact are used typically when we are looking at protein drug interactions in drug discovery, in protein structure analysis and ligand to protein binding and so on. So, we will start from first one today. So, that is chemical exchange. So, let us see what is a chemical exchange. Chemical exchange is nothing but a simple exchange of hydrogen atom between two different states of a system. So, if you look at this, for example, here we have labeled it as a molecule. So, consider this whole thing as a molecule, which we can call it as state A, and this has some hydrogen atom schematically shown here. Now, this state or this molecule suppose undergoes a change to another molecule, which may be the same molecule or a different structure or different molecule. There the same hydrogen now is represented like this, and this hydrogen now we can label it as state B, and this is a dynamic exchange. That means, this whole state molecule, this hydrogen atom goes from state A in this molecule to state B in this molecule and comes back to the original state and goes forward and back. So, this is like an equilibrium steady state system. So, we can call it as forward rate of exchange and a reverse rate of exchange. So, and this exchange rate is measured in the units of second inverse. This is typically the Hertz scale also, which we use for frequency. So, now what is the whole game of chemical exchange all about? The chemical exchange basically tries to study in NMR what is the rate of this exchange, how fast is this exchanging between these two, or is it a very slow exchange and so on. So, characterizing the rate of change of a hydrogen atom from one state to another state, that process comes under the purview of chemical exchange, and this has lot of applications, which is shown here. A few examples. For example, when you are studying ligand to protein interaction. So, suppose your ligand is state A, this hydrogen atom is attached to a ligand. Now, this ligand goes and binds to a protein, and this whole box here could be the protein plus the ligand, that is a bound form, and in the bound form the same hydrogen now can be called as in a separate another state B. So, ligand environment, it is in an environment around the free ligand. Here it is still attached to the ligand, but it is now the ligand is bound to the protein. So, this hydrogen now experiences a different chemical environment, and that is called state B. So, this is one of the first cases which we will come across. Ligand protein interactions is maximum, and the way the chemical exchange is useful, and typically when you look at drug to protein interaction or drug to receptor interaction or enzyme substrate interactions, all of this can be studied by this process of chemical exchange. Second possibility where it can be used is conformational change. And for example, let us say there is a protein which undergoes a conformational change from one state to another state. So, how do we talk about that? So, for example, let me go back to the previous slide. Here we saw this particular protein, or let us say this helix which you are seeing here, which is known as alpha 2. Suppose this helix is moving little bit left and right like this. It is basically having a dynamic motion. Okay. So, if that happens, that can be called as chemical or conformational exchange. Okay. So, a hydrogen atom sitting on this helix, one helix here, and a hydrogen atom on the same helix, but when the helix moves out can be called as a second state. So, this is called conformational exchange, and that is also very useful to study using this phenomenon of chemical exchange. Then in chemistry we often come across keto-enol tautomerism, where we can say that the keto form, the proton which is in the keto form, you can say state A, one state, and the same proton, same hydrogen atom in the enol form can be called as state B. So, remember we are always looking at the same hydrogen atom between one position to another position. So, we are not looking at two different hydrogen atoms, we are going to monitor the same hydrogen atom, how it behaves from one state to another state. So, the same hydrogen atom which is keto form will also now become an enol form, and the same hydrogen now will have a different chemical environment, and therefore, there will be a exchange of the environments between the two based on this kind of a chemical equilibrium process, and that now can be studied by NMR using the ideas of chemical exchange. And one of the other very important example, hydrogen exchange. This is very commonly used in peptides, proteins, or even small organic molecules, where we study how the hydrogen atom moves from the solute to the solvent. For example, a hydrogen atom, let us consider this case. Let us suppose this blue color circle is a molecule. So, the hydrogen is attached to the molecule, but that hydrogen now goes and exchanges with the solvent. So, suppose this square is a solvent here. So, the hydrogen atom from the solute goes and attaches to the solvent. So, that is a different molecule now. It is sitting on the solvent, here it was sitting on the solute. So, this hydrogen atom therefore experiences an exchange or a interchange between the molecule and the solvent. So, this process, if it is fast or slow, can be characterized by NMR, and that gives you a lot of information about the environment of this hydrogen atom. Let us say suppose it is involved in hydrogen bonding with some other hydrogen in the molecule. If that is so, then this hydrogen will not like to move to the solvent. So, its exchange rate from here to here then will be slow, because it is hydrogen bonded to some other hydrogen. So, it is not available for exchange. So, based on these exchange rates, we can now figure out whether this hydrogen is hydrogen bonded or not, or is it buried inside the molecule or not, and that information becomes very useful to have if you want to look at structures. So, hydrogen exchange is a very important experiment which is carried out by NMR to find out the state of the hydrogen bonds. So, when we look at chemical exchange between two states, we talk about three different types of exchange. Number one, it is called slow exchange. Slow exchange means this hydrogen is going slow between these two, but remember, slow or fast is only relative. So, what is it related to? Means I cannot, there is no absolutely we can say there is slow or fast, it is always relative to something that the exchange can be called as slow or fast. So, that is what is shown here, that we talk about slow exchange when the exchange rate between the two hydrogen is. So, let me write this down here. So, we will talk about slow exchange. So, what is slow exchange? A slow exchange is when the exchange A to B or B to A is much slower then the difference in the chemical shift between A and B. Okay. So, this is a very important parameter in terms of, we say slow exchange, slow on the chemical shift time scale. Okay. So, we can say that these two hydrogens, these two states, this and this, are undergoing slow if the exchange rate between them, the value of the exchange rate is much smaller than this. So, remember this is in ppm. So, this has to be converted to hertz. So, how do you convert this into hertz? You have to multiply with the spectrometer frequency. Okay. So, for example, let us say the exchange rate, let us take an example. Suppose the exchange rate, I will call it as K exchange, which basically sometimes is the sum of these two. Suppose the exchange rate is, let us say, 5 per second. That means the molecule jumps between A to B 5 times in a second, and let us say the chemical shift between the two peaks. So, let us say this is 5.1 ppm and suppose this is 6.1 ppm. Okay. So, now what is the difference? The delta A minus delta B, if you take the modulus, is 1 ppm, which is, suppose let us say we are doing at 500 megahertz spectrometer, then it will be 500 hertz. Okay. So, now you can see satisfies this condition, because 5 per second is definitely much smaller than 500 hertz. So, then we can say that these two hydrogens are undergoing a slow exchange, means they are going a slow. So, slow is always relative to the value, the difference in the chemical shift between the two atoms A and B, the two states A and B. So, in state A it will have one particular value, in state B it will have another value. That means they should definitely have two different values, they cannot have the same value or nearby. If it is nearby, then this condition is not satisfied. So, if it is far away, far in the sense the difference in hertz value should be small, should be large compared to the chemical shift exchange value, rate value. So, this is how we say whether an exchange can be considered as fast or slow. Suppose the distance between these two atoms in the chemical shift, suppose that it is very small, suppose this is 5.9 and suppose or 6 ppm, suppose this is 6 ppm and this is 6.1, then your difference is only 0.1 ppm. Now, 0.1 ppm on 500 megahertz is 50 hertz. So, even 50 hertz is still much bigger than 5 hertz, but suppose the K exchange is also 50. Okay. So, let us imagine that K exchange means that hydrogen atom jumps from here to this molecule 50 times in a second. So, it is 50 hertz. Then the chemical shift exchange, suppose this is 6 ppm and 6.1, then the difference is 0.1 and 0.1 ppm on 500 megahertz is 50 hertz. So, 50 and 50 both become almost equal, then this condition is not satisfied. So, therefore, we have to consider that as a different type of exchange, and that is called as intermediate exchange. So, intermediate exchange is a scenario where the exchange rate comes very close to the difference in the chemical shift, which is calculated in hertz. And if you go further, suppose now the exchange is opposite, it is very fast compared to the difference in hertz, then that is called as a fast exchange. So, in an intermediate exchange, so we will look at in the next class, having looked at these 3 different regimes, we will see how the peak shapes which are shown here can be explained in a fast exchange and a slow exchange regime. So, this we will continue in the next class.